This is the 6th lecture of the course MTH 204A for section B. In the last lecture, we have been introduced to group actions and we have seen some examples. In this lecture also, we will talk about some more examples. More importantly, they will be from diverse areas of mathematics like geometry, number theory, dynamics, etc. The first example we are going to talk about is purely algebraic in nature. Let G be a group and H be a subgroup of G. By this notation, we denote the set of all left cosets of G in H. We are now going to see a natural action of the group G on this set. So, namely, the following, that is for a group element G and a coset XH. So this pair is going to be sent to the coset of the group element Gx. It's easy to see that the kernel of this homomorphism is this subgroup of G, which is in fact the largest normal subgroup of G contained inside the given subgroup H. The second example is from geometry. Denote by C union infinity by C hat. So if you know what stereographic projection is, then you see that this is actually can be visualized as this as a sphere, and that is why we call it the Riemann sphere. So the following defines an action of GL2C on the Riemann sphere denoted by C hat. So a matrix ABCD, an invertible 2x2 matrix ABCD, sends up an arbitrary point Z to this AZ by B upon CZ plus AZ plus B is upon CZ plus D if Z is neither equal to minus D by C or infinity. And if Z equal to minus D by C, then it sends Z to infinity. It sends to infinity, and if Z is infinity, then it is being sent by the matrix to the to A by C. It is easy to see that this defines an action of the GL2C on C hat. This action is called the action of GL2C on the Riemann sphere by Mobius transformations. So the reason for calling this action as an action by Mobius transformation is the maps of this form, the transformations of this form. So it's a function in one complex variable. So the functions of this form are called linear fractional transformations or Mobius transformations. You will see, most likely you will see these functions in your complex analysis course. So since these functions or transformations are called Mobius transformations, that is why we say that this action of GL2C, the action on C hat by Mobius transformations. And since GL2C acts, then automatically we get an action of SL2C on the Riemann sphere C hat. Now let H stand for the upper half plane, that is the all complex numbers having imaginary part positive. So geometrically in the upper half, geometrically in the organ plane, H is this area, the upper half plane. Note that it excludes the real axis, and it is now easy to see that for any 2x2 invertible real matrix and a point Z in the upper half plane, if we look at the imaginary part of this quantity AZ plus B by CZ plus D, then it's a routine verification that the imaginary part is becomes this. So this is the imaginary part is nothing but the imaginary part of Z divided by mod CZ plus D whole square, which is of course positive because imaginary part of Z is positive. Thus what we see is what we see is this upper half plane is invariant under the action of SL2R. Let me again repeat. So earlier we saw that GL2C acts on the Riemann sphere. From that we get the action of SL2C on the Riemann sphere. Now we further focus on the subgroup SL2R inside SL2C, and then therefore SL2R also acts on C hat, and under this action we see that the subset the subset upper half plane of C hat is invariant. I repeat that under the action of SL2R on C hat, we see that H is invariant. Therefore, we immediately get an action of SL2R on the upper half plane H. So this action we also call as the action of SL2R on H by Mobius transformation. Okay, because here indeed the maps are Mobius transformations of the complex plane, and you see that for every complex number Z, for every complex number lying in the upper half plane, this quantity is meaningful because Cz plus D can never be 0. Okay, as Z is not allowed to be a real number. Okay. The next thing that we observe is that for every G in SL2R and H in the upper half plane, GZ is same as minus GZ. Because in case of minus GZ, you will have minus A Z minus B divided minus CZ minus D, which is exactly same as GZ. So therefore, we see that every group element G and minus G, these two group, for any group element G and minus G both are acting upon H in the same way. So thus from this it follows that the group defined, this projective special linear group, which is defined as SL2R factor plus minus identity, also acts on H, because this subgroup plus minus identity lies in the kernel of the action of SL2R on H by Mobius transformations. Okay. Now we are going to see the action of this group SL2R and consequently PSL2R on the tangent bundle of the upper half plane. So for each Z in Z, we define TZH. So we are going to call TZH as the tangent space of the upper half plane at the point Z. So we define TZH as this, that is singleton Z Cartesian product with the complex plane C, and then we further define TH. TH is to be the H Cartesian product C. So it is easy to see that this is nothing but the disjoint union of all tangent spaces. Okay. So this is what we are going to call as the tangent bundle of the upper half plane. Now for every group, every matrix GA equal to ABCD in SL2R and Z in the upper half plane, we have for every G and Z, we are going to have a linear map from the tangent space of the upper half plane at the point Z to the tangent space of the upper half plane at the point GZ. I repeat, so try to understand that for any G and Z, we are going to define a linear map from the tangent space at Z to the tangent space at GZ. So how is that map defined? We denote this map by DG at the point Z. So a typical point here, which is of the forms which is a pair Z comma V, is now being sent to. So of course here the first coordinate has to be GZ, and the second coordinate is V by CZ plus D whole square, where G is equal to A, B, C, D. So for each G and each Z we have a map for so for each G and for each Z we are going to have a map from the tangent space at the point Z to the tangent space at the point GZ. And from this we are now going to define a map which we call the differential of G for every G. So it's a map from the tangent bundle to the tangent bundle defined in this way, that is for any G, for any just a minute, so for any point in the tangent bundle Z comma V, it is sending this pair to DGZ comma Z comma V. So remember that how DGZ is defined. Okay, so thus this is nothing but GZ comma V by CZ plus D whole square. Okay, so for each G we obtain a map from the tangent bundle of the upper half plane to itself defined in this way. And finally, this gives rise to the following action of the group SL2R on the tangent bundle. So how is this action defined? Given a pair G and an element from the tangent space Z comma V, it is sending this Z comma V, this pair, to DG of Z comma V. So here DG is defined like this. So what is this ultimately? This is nothing but, so G comma Z comma V goes to GZ V CZ plus D whole square, where G is A, B, C, D. Okay. All right. So so now it's a trivial verification. Not trivial, rather I should say that it's a routine verification. But not at all difficult. It's a routine verification that this way we are going to get an action of the group SL2R on the tangent bundle of the upper half plane. Okay, so let me again summarize what we have discussed just now. So we have seen that SL2R acts on the upper half plane. And from that action, so the action of SL2R on the upper half plane is by Mobius transformations. Then we lift that action to the tangent bundle of the upper half plane. Okay. So the reason for calling it a lift is basically, though that's not quite necessary here, but however I can briefly tell you that we do have a map from H to H. So what is this map? Given a point GZ comma V, we can simply project it on H. Now for any Z, we have this map from H to H that sends Z to GZ. And on the other hand, here also we have this map DG. So the DG of Z comma V, so it's DG sends Z comma V to TH, right? So what's the first component of DGZ comma V? You see this is GZ. So therefore now when I again project that, it will come to GZ. So the reason for calling it this action of the SL2R on the tangent bundle, a lift of the action, is precisely the reason is precisely the commutative diagram for every G. That is, so you start with a point on the top, then you move it by DG. Where you get it? If you then project it downwards, that is same as first you project the given point downwards, and then you move it by G. You are going to arrive at the same place. Anyway, so that's just a technical remark, not necessary regarding actions. Okay. Now we are going to see that this action of SL to R on the tangent bundle of the upper half plane, then that gives rise to a map, an action of the same group on the unit tangent bundle. So before that we should define what a unit tangent bundle is. So note that for any given H, this admits a natural complex vector space structure. And if you have noted that when talking about this map, I somewhere said that this map is in fact a linear map. So in order to talk linear map, of course, I should have mentioned how these are being made vector spaces. That's exactly the point here. So if we regard the natural vector space structure on this, then it's now quite clear to us that this map is for any G and Z. This map is in fact a linear map from this vector space to from this vector from this vector space to from that vector space. Anyway, so the tangent space at every point Z has a natural vector space structure. It's in fact a one-dimensional complex vector space structure, and therefore it is equipped with a natural inner product. So how is that inner product defined? So the inner product is defined that if we take any pair here, Z comma V and Z comma W, then this new inner product is going to be defined. So just let me just change. So let's change it a little bit. So this admits a natural complex vector space structure, right? So one-dimensional complex vector space. We are now going to define an inner product on this tangent space at Z in the following way. So we denote the inner product by to specify, well, from the definition itself, you will see that why we need to specify this Z here. So for each Z, we are defining a new inner product on this tangent space of the upper half plane at the point Z. So how is that inner product defined? So we just take the usual inner product of the complex numbers V and W. So this is just the usual inner product. This is the usual inner product on C, and then we just scale it by this imaginary Z square. So again, let me explain the situation. Of course, you can say that since this is a one-dimensional complex vector space, by just by its natural identification with C, we can put the most natural inner product on this space. Of course, that we can do, but here instead we are doing something else. We are taking the most obvious choice of the inner product on TZH, but together with we scale it by this factor. Okay. So this scaling, the importance of this scaling you will see later on. So yeah, so since this is just a scaling of the usual inner product, just the scaling of the usual inner product, so it's easy to see that this also defines an inner product on this vector space TZH, and now you will see the reason for this scaling. The reason for this scaling is, if we consider this inner product, that is the usual, the obvious one, scaled by this factor, then we see that this inner product is going to be preserved under the action of the group SL2R. So for that, let's observe that for any G in SL2R and Z in H, we are, and for any two vectors V and W in C, one has that DGZZV and DGZZW. So what is, so this is nothing but, so this is nothing but Z by V CZ plus D whole square, and similarly this is also this is also nothing but, well, so again let me remind you that this is how they are defined. So this quantity is nothing but, by definition, gz, so this quantity is nothing but, by definition, just a minute, gz by v by cz plus d whole square, and here this again, this is the same thing, gz by w by cz plus d whole square, right? So this should be this should be the inner product here, and by definition this is nothing but the usual inner product. So just a minute, just to make sure that there is absolutely no problem with the definition. Yes, so like here I dropped the in here I dropped gz from both the components for simplicity, but anyway it is clear that this is going to be the usual inner product of this complex numbers and scaled by the imaginary part of gz, which we have already seen to be this, right? So therefore the usual inner product of these two vectors, which is nothing but the inner product vw times this, and then it is further scaled by this. Now this is easily seen to be this. So by definition is again the inner product of gv, inner product of zv and zw. So yes, like here for simplicity I note that again, so dgz should be a pair whose second component is this. Similarly this also is a pair, his second component is this. The first component of both of them will be gz. For simplicity I have dropped gz from the notation. Maybe while uploading the PDF I can add the first component if you like that better. Anyway, so the crux of the point is, for any z and for any g and z, the map for any g and z, the map dgz. So dgz is nothing but a map from tgzh. So for any g and z, we see that this map preserves the inner product. That's all we have shown here. Okay. So as a result of this, since this map is preserving the inner product, so again for any g and z, the map dgz, since it is preserving the inner product, okay, so therefore it will preserve the unit vectors, that is image of a unit vector here goes to will be a unit vector here, okay. So from this it is quite clear that this set, that is the all pairs that's all pairs z comma v, such that this is 1. So what is this? So for simplicity so this quantity is nothing but the norm of the pair z comma v. For simplicity, like earlier, I have deliberately dropped z from the first first component. So basically this consists of all unit vectors from all the tangent spaces, okay. So let me again repeat, corresponding to every z, we have collected all the tangent corresponding to every z, we have collected all the unit vectors in the tangent space tzh, okay. So thus for all z, this is the for each z we have collected all the vectors in the tangent space having unit norm, okay. That once we do this for all z in the upper half plane and collect them together, this is what we are going to get. This is called the unit tangent bundle of the upper half plane. That is precisely the collection of all unit vectors from all the tangent spaces. Okay, and remember that it's necessary to mention z here, because on each tangent space the inner product that we are going to consider depends upon the choice of the inner product depends upon the point z. Okay, so that is how so this is the collection of all unit vectors in all the tangent spaces of the at all the points of the upper half plane. And what we have seen here, that if we rephrase that in terms of this unit tangent bundle, what we can immediately say is this collection is invariant under the action of SL2R. Okay, because we take any unit vector in the unit tangent bundle. So any unit vector in the unit tangent bundle, so that will also go to an unit vector. So if we choose any unit vector z comma b in the unit tangent bundle, its image is going to be this, which will also be a unit vector. So thus this set is invariant under the action of SL2R. So from the so therefore we do have a natural action of this 2 by 2 group of real matrices with determinant 1 on the unit tangent bundle of the upper half plane. And like earlier, we can immediately see that for any G, so for any group element G and minus G both act on this both act on TH and of course and consequently on T1H, both act same on TH and consequently on the unit tangent bundle. Therefore, from the action of SL2R on the unit tangent bundle, we get the action of the projective special linear group as well. So let me again summarize this example. So basically we can divide it into 3 steps. In the first step, we have seen the action of the GL2C on the Riemann sphere. Then from that we obtain the action of SL2R on the Riemann sphere, and since upper half plane is invariant under this action of SL2R, we get an action of SL2R on the upper half plane. Then we lift that action to the action of SL2R on the tangent bundle of the upper half plane, TH, on the tangent bundle of the upper half plane, and then finally from that we obtain the action of the same group on the invariant on the unit tangent bundle, as it is invariant under the action of SL2R on the action of SL2R on the tangent bundle. So first we have action of SL2R on the upper half plane. Next we have the action of SL2R on the unit tangent on the tangent bundle upper half plane, and finally we have the action of SL2R on the SL2R on the action of the on the unit tangent bundle of the upper half plane. And from the actions of SL2R we immediately obtain the actions of the projective special linear group PSL2R as well. All right. The next example is about the action of special linear groups on the space of lattices. So recall that for any natural number n and any k less or equal to n, a discrete subgroup of Rn of rank k is basically the subgroup of Rn generated by a linearly independent subset consisting of k vectors, that is by a discrete subgroup of rank k of Rn, by a discrete subgroup of Rn or having rank k, we mean a subgroup of this form where V1, V2, Vk is a linearly independent subset of Rn, and we to have the action of the general linear group on the set of all discrete subgroups of rank k for any k, namely a matrix A and the discrete subgroup k is this pair is being sent to the image of the discrete subgroup gamma by this linear map, invertible linear map A. So since the image of a discrete subgroup is again going to be a discrete subgroup, so that indeed defines an action here, and that's how we obtain the action of GL and R on the collection of all discrete subgroups of Rn of rank k. Now a discrete subgroup of full rank is called a lattice in Rn. Okay, so that means a lattice in Rn is a subgroup of this form, that we start with the basis of Rn and then we take its Z span. Okay. Now before I go ahead, I need to leave this to you to settle. That is, given a lattice gamma, whatever basis you choose, this quantity is not going to change. Okay, given a lattice in lattice gamma, that then this quantity, that is determinant of this, absolute value of the determinant is not going to change whatsoever basis of gamma you choose. And that's actually immediate. If you remember that two bases of a discrete subgroup, and in this case of full rank, they differ by a matrix with integer coefficients, and a matrix with integer coefficients which is also invertible, and the inverse is also having integer coefficients. Therefore, such a matrix which has inverse a matrix whose inverse, a matrix with integer entries whose inverse is also having integer entries, must have determinant plus minus 1. So in view of that, it's immediate that this quantity does not change upon the choice of the basis. So therefore, since this doesn't depend upon the choice of the basis, we may call this we can give this quantity some name. So here it is called the co-volume of the lattice gamma. So let me just explain that by an example. So why this word is volume is there. So let's say in Z2, let's say in R2, if you consider the standard lattice Z2, okay, standard lattice Z2, then you see that this is nothing but the area of this. Okay, so this area is called the co-volume of the standard lattice Z2. So if a lattice has co-volume on, then it is called unimodular. And for example, as I just mentioned, that for any n, the standard lattice Zn is unimodular. And so now we denote the collection of all unimodular lattices in Rn by this Ln. So Ln is the collection of all unimodular lattices, that is the lattices with co-volume 1. Let me again remind you, by the co-volume of a given lattice is very simple, that you choose a basis of the lattice, then first consider this determinant and then take its absolute value. Now it's a routine verification that if for any matrix with determinant 1 and any unimodular lattice gamma, then the image of the unimodular lattice under this linear map is also going to be an unimodular lattice. That's just a trivial computation. So therefore, we obtain the natural action of SL and R on the space of all unimodular lattices. So let me again explain what is happening, that we have the action of GL and R on the set of all discrete subgroups of any given rank K. In particular, as GL and R acts on the space of, on the set collection of all on the space of all lattices in Rn, and from that we obtain the action of SL and R on the space of all lattices in Rn. And in this action of SL and R, we see that the space of all unimodular lattices, that subset is invariant. Therefore, thus we obtain the action of SL and R on the space of unimodular lattices. So this action we will encounter quite often in homogeneous dynamics. Okay, the next example is about the action of the general linear group on the space of all bilinear forms. So given a vector space V over F, recall that a bilinear form is a linear function from V cross V to V, which is linear in either of its variable when the other is fixed. Given V, the set of all bilinear forms is denoted by L2VF. It's easy to say that it's a vector space over F. And let's consider invertible linear map on the vector space V. For an invertible linear map P on the vector space V, we define for an invertible linear map and a bilinear form, we define PF as follows. So for any x and y, PF of xy is defined at f of P inverse x and P inverse y. And first of all, it's quite easy to see that PF thus defined is a bilinear form on V, and hence that provides the action of GLV on L2VF. Okay. So here I would like to make the following remark, that for any k we can define the action of GLV on the space of all k linear forms on V exactly in the similar way. So what I mean is, like here you see, it's not at all important that there are two components. If there would be k components, then we could have written the same for k many components, and we could have written the same for k many components, and of course that would give us another k linear form, and thus we can obtain the action of this general linear group on this set of all k linear forms on F. Okay. The next example is about the action on the quadratic forms, real quadratic forms. So for any n, consider a real quadratic form Q in n variables. For any invertible matrix G, let GQ be the quadratic form defined as follows, and it's immediate that G comma Q goes to GQ. This defines an action of GL and R on the space of all real quadratic forms in n variables. So here I would like to leave the following as an exercise to you, that under this action of GL and R on the space of all real quadratic forms in n variables, under these actions, these subsets are invariant. So the first one is the all positive quadratic forms, or some authors call it positive definite quadratic forms. Similarly, negative quadratic forms. Well, of course, instead of positive quadratic forms, you can also go for positive definite quadratic forms. Similarly, negative definite quadratic forms. Now the third one is the collection of all indefinite quadratic forms, that is neither it's positive form nor it's a negative form. So that is, there is a point, non-zero point, where the quadratic form has value positive, and as well there is another non-zero point in Rn where the value of the quadratic form is negative. The last one is this all non-degenerate quadratic forms. So non-degenerate means it is never going to be 0 unless x is 0. Equivalently, the matrix of this quadratic form will be non-singular. So it's basically these are quite easy verifications. So we will move on to the next example. So in the next example is let's start with the vector space V, and for each V in V we define the map which is the translation by the amount V, translation of the vector space V by the amount small v, and we consider, it's easy to see that all these maps are invertible. The inverse of TV is T minus V. Now we consider the following collection. So this is the collection of all maps of this form. So it's an invertible linear map followed by a translation, and it's easy to see that this collection is indeed a subgroup. So we call this the affine general linear group of V. So the reason for calling it affine is, so what is affine general linear group? It is nothing but the later on we will see that this affine group can be obtained as a semi-direct product, but let's not get into that. So what is an affine general linear transformation, or affine invertible transformation, or some authors call it invertible affine transformation? So this is nothing but an invertible linear map followed by a translation. So now we are going to talk about actions of this affine general linear group. So one thing we should observe that the group of the collection of all translations, it is indeed a normal subgroup of this affine general linear group. So before we look at the actions of this affine general linear group, let's consider a special case of this, when V is this vector space Fn. Then it is easy to see that this affine general linear group is isomorphic to the following subgroup of so this is a subgroup of GLN plus 1F. Okay, it's isomorphic to the following subgroup of GLN plus 1F. Okay, now we concentrate upon the actions, upon the following actions of this affine general linear group. So for any k, let's consider the collection of all k-dimensional affine subspaces of dimension k. So by an affine subspace, if you remember that it is it's just a subspace followed by a translation. So then this affine general group acts on the space of affine subspaces in the following natural way. So the thing is that earlier we have seen that for any given k, the general linear group acts on the collection of all k-dimensional subspaces. Now the affine general linear group acts on the collection of all k-dimensional affine subspaces. And the action is in the natural way, because under affine transformation, image of an affine subspace is again an affine subspace, because an affine transformation is nothing but a linear map followed by a translation. Alright, now we are going to talk about the affine affine general linear group. We are going to talk about affine special linear group. So we assume V to be finite dimensional for any linear operator, for any linear operator T on V, we define its determinant to be the determinant of the matrix of T, matrix of T relative to any ordered basis B of V. And of course we have to make sure that this quantity does not depend upon the choice of this ordered basis. That actually follows from the fact that similar matrices have the same determinant. So I leave the detailed verification to you. So show that this quantity does not depend upon the choice of the ordered basis B. So having settled that, we can safely define determinant of T to be this for any ordered basis B of V. And once I've defined the notion of determinant of a linear map without any ambiguity, then we can consider the collection of all linear maps whose determinant is 1. This is of course a subgroup of GLV, and as like earlier we can then consider ASLV. These are nothing but the maps with determinant 1 followed by a translation. It is easy to say that this is a subgroup of AGLV. That's quite immediate. We call it, so this group is called the special linear group, and this is called the affine special linear group of V. And since this is a subgroup of AGLV, so it also acts on the SK, which is the collection of all k-dimensional affine subspaces. Now let V be a finite dimensional real inner product space, and then we consider this collection of So here A is an orthogonal linear map. So this is a subgroup of AGLV. We have seen this subgroup earlier. This is nothing but the group of all isometries of V. Okay. So by an isometry, remember that by an isometry we mean maps which preserve by an isometry I mean a map which preserves the distance between any pair of points in V. And since this is an isometry, from that we see that this group of all isometries this group has natural actions on the following sets. First of all, it will act on SK because AGLV acts on SK, and this is a subgroup of AGLV. So it is nothing, I would say it's nothing special. Rather, the geometric one is the following one, just a minute. Yeah, so geometric one, rather the geometric one is the following one. So for fixed positive integer r, positive number r, and consider the collection of all closed balls or open balls or circles of radius r. So let me remind you what this means. So the closed ball with center x and radius r means this. An open ball with center x and radius r is this, and this is the definition of the circle with center x and radius r. So since any map here is an isometry, it is easy to see that this group, that is the group of isometries of V, that acts on the collection of all closed balls of any given radius. Similarly for the open balls of a fixed radius, and the collection of all circles of some fixed radius. So the radius is to be fixed because any map here is preserving the distance between any pair of points. Okay. So next example is again quite geometric, and you will be able to, I hope that you will be able to realize that you have seen this earlier in your school days, but now it is being presented in a somewhat form in a somewhat formal and modern language. So here we consider a plane that is a vector space with dimension 2. A subset PQR with PQR non-collinear is called a triangle in V. So the reason for calling it triangle, you see that it indeed given any 3 points PQR, since they are non-collinear, you can immediately see a triangle in the usual sense with these 3 points as vertices. And similarly, we can define a quadrilateral. So an ordered quadruple is said to be a quadrilateral if no 3 of these points are collinear. PQRS. So again, the reason for calling it a quadrilateral is obvious. Since no 3 points are collinear, you can immediately visualize a quadrilateral in the usual sense, right? And a quadrilateral PQRS is said to be a parallelogram if it's pairs of, so if you consider any pair of the opposite sides, then they will be parallel. Now on these collections, we are going to see the following natural actions of the AGLV, that affine general linear group on V. So first observe that if you have a triangle and then the image of a triangle under an affine invertible affine transformation is again going to be a triangle. So let me, just to make it precise, let me just tell you that how this is defined in the very natural way. If the triangle is PQR, then this is defined as FP, FQ, FR. Okay, it is defined like this. Similarly for quadrilateral, so it's easy to see that if we are given a triangle and an F, then the image of this triangle under F, under this affine transformation, again a triangle. Similarly, image of a quadrilateral under an affine transformation is a quadrilateral, and image of a parallelogram under an affine transformation again going to be a parallelogram. Okay. So thus, in view of these exercises, it's quite clear that AGLB has natural actions on this collection of all triangles in V, on the collection of all quadrilaterals in V, and the collection of all parallelograms in V. So this is quite. I hope that you are able to recognize that these things you have seen earlier. Like in your school geometry course, we used to transform these geometric figures. So that is, suppose 2 triangles are given, then we try to rotate a triangle or reflect a triangle with respect to something, and then translate, and then in order to compare that with the other given triangle. Similarly for quadrilaterals, parallelograms. So whatever you have done in transformation geometry, that is exactly put in the formal language here, formal language of linear algebra. The formal language linear algebra and group actions in the here, and nothing else. So so in this terminology, if for some suitable f, given 2 triangles delta and delta prime, if for some suitable f, if we can do this, then we would say that the triangles delta and delta prime are congruent. Okay, so as I said, the same thing is now being presented in a different language. Okay, the next example is a quite easy one. So earlier we have seen that for any vector space V, it admits an action of the multiplicative group of the field. Okay, so now we are going to see an action of the additive group F on the space V. So how is that? So we fix a vector W, and given any vector V, we translate that vector. So given any vector V, we first fix some W, and then for any vector V, we move. So let me again try to explain. So we have fixed some vector W, then for any other vector V, we will move the vector V in the direction of W by the amount alpha W. Okay, so given a vector V, we will move the vector in that direction by this amount. It's easy to see that that gives us an action. The next is basically an action of one of the most familiar infinite group Z. So if we consider a bijective mapping on a set non-empty set X, then that is going to give us an action of Z on X using this map. And in fact, every action of Z on this given X is necessarily of this form. So what I mean by that is, given an action of Z on X, there is a unique bijective map such that the image of n comma x should be this. Okay. Well, so far so good. Let's now go ahead. For any abelian group G, we now see that it has a natural action of this group Z modulo 2Z, which is in fact isomorphic to the multiplicative group plus minus 1. So how is that action defined? It's an immediate one. So in fact, the better way to see this is that we regard Z modulo 2Z as by this multiplicative group. So thus 1 sends each x to x itself, and minus 1 sends any x to minus x, to x inverse. Okay. Yeah. In fact, if we view this as the minus plus minus 1x, then this action becomes easier to see. And furthermore, if S is symmetric with respect to this inversion, that is, whenever x is in S, then x inverse will also lie in S, then automatically the group gene, then S is gene variant. So I think there is a mistake. I should in fact say there is not Z invariant. This is rather Z modulo 2Z invariant, and here also Z modulo 2Z acts on S. Okay. In particular, we have the action of Z modulo 2Z on the n-dimensional sphere. So what is Sn? Sn is nothing but this collection. So for example, when n is 1, S1 is the usual circle, S2 is the sphere in R3, the two-dimensional sphere. Similarly, this is the general n-dimensional sphere. So this is a subspace of Rn plus 1. Okay. And we do have an action of Z modulo 2Z on Sn. The next few examples of actions that we are going to see are basically coming from representations. We will talk about representations in details in the next lecture. So, given a group G and a vector space V, a homomorphism from G to GLV is called a representation. Okay, or representation of G on V. So whenever we have a representation of G, then whenever we have a representation of G on V, then automatically we obtain an action of G on V. So how is that defined? So for any G and V, we send this pair to rho G of V. for also one noteworthy point here is for each G the map rho G is linear. So basically G acts on V by linear automorphisms. So as a special case of this, we obtain the following actions. The first one is for any n, we obtain the action of z modulo nz on the complex plane, because because from z modulo nz to C star we have this very natural mapping. So for any k, for any k, we send the group element to this complex number. So in view of this homomorphism from z modulo nz to GL of C is nothing but C star. So from that representation we get this action of z modulo nz on C, and in fact working component wise we thus obtain an action of z modulo nz on CD for any positive integer d. So how is that done? That we first fix any d number of integers, and then a tuple mz where z is around to zt is being sent to this. Now we look at we talk about the following action of the Klein 4 group V4. So the Klein 4 group has the following action on C2. So again, how is this action? So how to look at this action? So that's very simple, that from the Klein 4 group we do have the following. This Klein 4 group we do have the following homomorphism into GL2C. So we send E to identity, A to let's say -1 0 1, B to -1 0 -1, and C to I think let's see. So I think So here I should have written C, and rather therefore B should be sent to 1 0 0 -1. So it's easy to see that this gives a homomorphism from V4 to GL to C, and that gives us this action. All right, and So these are the actions of the cyclic groups. Now we will finish this lecture with the following actions of the group of real numbers. So fix real numbers alpha n up to alpha n, then we can each real number t, if we send that to e to the power alpha 1 t diagonal e to the power alpha n t, then certainly it is going to be a homomorphism from R2 to the group of all invertible diagonal matrices. And with respect to this homomorphism, and with the help of this homomorphism, we obtain this action of R on Rn. So this action is called diagonal flow. Let me remind you that the actions of R, or more generally the actions of the semigroup of non-negative reals, are called flows. So this is called a one parameter diagonal flow. The reason for calling it one parameter is intuitively clear, because this is basically this e to the power alpha n t. So like the action is being governed by the single parameter t. Now we look at another action of R, which is on R2. So consider this homomorphism 1 t 0 1 is a homomorphism from R to GL to R. With this homomorphism, the action on R2 that we obtain is exactly this. So this is called a one parameter unipotent flow. the reason for calling it unipotent is all these matrices are unipotent matrices. Let me remind you that unipotent matrix is the matrix which has all eigenvalues 1. So this action is called the unipotent. One parameter is an example of a one parameter unipotent flow on R. So the general meaning of one parameter unipotent flow you will see later. Let's not get into that. So the last examples are important examples of flows which we will encounter quite often later on. Okay, so with that I will finish this lecture.